One of the additional problems in osteoarthritis or joint injuries occurs when an injury results in a complete loss of a piece of cartilage from the joint. That's called a focal defect. And again, this is unfortunately a very common injury found in sports medicine quite a bit. Right now, the gold standard of treatment in the clinic is to perform what's called microfracture, where there might be a region where there's bare bone and cartilage that's still left on the joint. The defect occurs where cartilage has come off a piece of bone. And when the surgeon pokes into the bone, marrow progenitor cells from the marrow can come up and regenerate a tissue. And that is commonly performed now all over the world. The problem with that approach, unfortunately, is that the tissue that's regenerated is not real hyaline cartilage, the same articular cartilage that we're born with. It's more of a fibrous wound repair tissue, which is great for several years because it can eliminate pain and allow you to articulate and move your joints, but eventually, because of the differences in the properties of that fibrous tissue from the surrounding normal cartilage, that fibrous tissue can wear away and you're back to where you started, perhaps in 5 or 10 years. Because of that problem, groups all over the world have been looking to find ways of tissue engineering repair tissues for cartilage. Unfortunately, there's not one lab or industrial group that has yet come up with a solution, but many of us are still trying different possibilities. Different scaffolds, hydrogels are being used, different approaches where the scaffold is pre-seeded with a cell in the incubator and then the whole tissue implanted, or a scaffold alone is placed on the wound site with the hope that marrow progenitor cells will migrate into the scaffold and set up shop and begin to generate a new tissue. So we're pursuing a line of experiments in this area in collaboration with an equine orthopedic veterinary group at Colorado State University. And ultimately, it's very important to do a range of animal studies. Whatever you try in the lab is never going to get anywhere unless they're tested. And it turns out that using horse models is extremely interesting and important, because if your tissue engineered cartilage can withstand 1,000 or 1,500 pounds of horse, then the hope is it might withstand being implanted in us. So where we are here at MIT, we're trying a particular hydrogel scaffold. It's a self-assembling peptide scaffold. In the lab, we take equine or bovine marrow cells, place them in the hydrogel, and students in the group have learned how to stimulate these cultures in such a way that the cells, which initially do not make any cartilage-specific molecules like aggrecan or type 2 collagen, they can be treated with a chondrogenic medium to stimulate chondrogenesis of these stem cells. And that process can be studied again at the level of cell and molecular biology, as well as using incubator-housed mechanical loading instruments, taking these cartilage tissue engineered materials and subjecting them to physiologic-like loading to see how that might accentuate and enhance the response, not just the timing, but the extent of development of new cartilage. So we have been taking our hydrogel, functionalizing it with various growth factors that might help to stimulate migration of stem cells. A student named Paul Libesny, who's going to be graduating, unfortunately, and therefore leaving our lab later this month, has been working on this and found a combination of growth factors that really helps to enhance migration of stem cells into the gel, and then other growth factors that are functionalized to the gel are helping to stimulate growth of the cartilage-like tissue in the gel, as well as to integrate that new tissue with the adjacent native cartilage that's there. One of the most difficult problems in tissue engineering for cartilage repair is no matter how beautiful your construct looks in the incubator, if it doesn't integrate with the surrounding native tissue, it's just not going to last, because mechanical loads that are placed over a material that has two very different mechanical properties, the native tissue and the repair tissue, is going to induce fracture right at that interface. So integration is a tremendous problem, and that's something that we're looking at, as well as many other groups. One might ask why we need cartilage in the first place. Why can't we just replace it with a polymer? And ultimately, that in fact might happen. Who knows, 50 years from now, we might have wonderful polymeric materials that are better than the current metal and plastic that are used as joint replacements. I'm sure we all know people that have had a hip or a knee replacement. And while those are wonderful solutions over 10 or 20 years, there can be problems. Suppose we blue sky 50 or 100 years forward, could there be an approach to having polymeric materials that behave just like our cartilage, that are not just nailed into place? That's something we're all thinking about. At the same time, I marvel at the intricacy and beauty of a tissue like cartilage. People have been trying to put polymeric materials over bone as substitutes for cartilage for a long time. It just doesn't work. It turns out cartilage is a self-stiffening material. When you stand on it, it presents a certain modulus, or ability to resist compression. When you run on it, the stiffness presented to the same loading is much more. That is, it's stiffer when the applied load is stiffer, and especially when the applied load is more rapid. So can we make materials that simulate that? So far we haven't been able to, and that's why people doing cartilage tissue engineering are still trying to replace cartilage. But maybe with the advances in material science, we'll be able to come up with an approach like that.